So tangent lines. We are going to be spending a lot of time in this course working with tangent lines. So a tangent line is a line that intersects a function once at a point of tangency. It's the idea that it just touches against the curve. So if this is my curve, an example of a tangent line would be this, where right here is the point of tangency. Or if I say, here is my point of tangency, that would be a tangent line. Tangents are always going to be lines, which mean you need to know two things to write their equation. A tangent line, you need to know the slope of the line, and you need to know a point the line goes through. The point that we are going to typically use is going to be the point of tangency. The slope of the tangent, which we will explore together in class, is the instantaneous rate of change of the function. And because we're always working with a point and the slope, point slope form is going to be the easiest way of doing this. So examples, or I'm sorry, before I get to examples, the normal line. If you are interested in physics, in some of the engineerings like mechanical engineering or civil engineering, you're going to be dealing with normal lines because you have quite a few forces in physics that are normal to other forces. So like gravity is a normal force. Centripetal force is a normal force. Normal just means it's perpendicular. So a normal line is perpendicular to a tangent line at the point of tangency. Again, it just touches the function, but it's going through the function rather than being just glancing against it. So if this is my function, this would be a tangent. And then this would be the normal. Because it is a line, you still need two things. You need a point, which will still use the point of tangency, and we need the opposite reciprocal of the slope of the tangent, which is the instantaneous rate of change of our function. We want the opposite reciprocal because it is perpendicular, and slopes of perpendicular lines are always going to be opposite reciprocals. And again, point slope form is recommended. It's not required, but it is going to minimize the chances of a careless algebra mistake. So first example, I want to find the equation of the tangent to k of x is equal to x squared plus 4x minus 1 at x equals 1. Well, my thought process is always, if I want the equation of a tangent, well, what shape is a tangent? It's a line. What are the things I need to know to write the equation of a line? I need a point and the slope. So rather than trying to find the whole line at once, I'm going to start by saying, should I find the point or should I find the slope? I'm going to start with point because it's going to be a little bit easier for me to find. So my point, the x is 1. Well, then I just plug 1 in for x to my function. So k of 1 is going to be 1 squared, which is 1, plus 4 times 1, which is 4, minus 1, that's going to be 4. So the point I'm using is 1, 4. And I've got half of what I need. Well, now for slope of the tangent, I need the instantaneous rate of change for this function when x is 1. I find it helpful at this point to just sketch a picture. I don't know exactly what this function looks like, and I'm too lazy to look at it perfectly. All I just need is just some visualization. I do know it's a parabola. So I'm going to just say, well, here's a random parabola. And here's when x is 1. Well, if I want the instantaneous rate of change, so this is at 1, 4, which I already found. I need a second point that is h away from the 1 horizontally. So that's going to be 1 plus h. If I plug that in here, I have 1 plus h for the x. I plug 1 plus h in for x in my function. So I have 1 plus h squared plus 4 times the quantity 1 plus h plus 1 as my y coordinate. So now for my slope, I can do change in y over change in x. So I have the 1 plus h squared plus 4 times 1 plus h plus 1 minus the 4 from the other point over the 1 plus h minus the 1 from the other point. And then I can do some simplifying. So we've got 1 plus 2h plus h squared, just multiplying everything out here so that I can then start combining like terms. The 4's are going to cancel. Oops, that's not a minus 1. Sorry, should be a minus 1, not a plus 1. Hopefully you caught my mistake. So the 1's are going to cancel. The 4's are going to cancel. I can do 2h plus 4h, so I get 6h plus h squared all over h. I can divide the whole numerator by h, which gives me 6 plus h. Now that's the slope between 2 points. I then need to move those 2 points close together so that the distance between them is approaching 0. And I can now do substitution, and I get the slope is 6. So I know the slope, I know the point, I can write point-slope form and say that my tangent equation is going to be y minus 4 is equal to 6 parentheses x minus 1. And there is my tangent line. If I want the normal at that same point, the only thing that changes in my equation is the slope becomes the opposite reciprocal. So my normal is going to be y minus 4 is equal to negative 1/6, so it's perpendicular, x minus 1. If I go to a second equation, or a second example, rather than writing the equation of a tangent, I just want to know where does the slope of this function r of x equals 1 over x equal negative 1/4. Again, if I'm finding the slope of this, that means I'm doing an instantaneous rate of change. So I'm just going to do a little sketch to help me visualize things. So I happen to know what 1 over x looks like. If you don't, you can just make a random curve. The problem here is I don't know what x value I'm supposed to be using. So I'm just going to pick a generic x value. I don't know it, so I'm just going to leave it as x. Well, that point here has an x coordinate of x. Plugging that into my function, my y coordinate is also 1 over x. To find the slope, I need a second point. So I'm going to move over a horizontal distance of h to here. So that's going to be an x plus h for the x coordinate. Plugging x plus h in for x in my function gives a y coordinate of 1 over x plus h. And now that I have 2 points, I can find the slope between those 2 points. So the change in y over the change in x is going to be 1 over x plus h minus 1 over x all over x plus h minus x, which to subtract 2 fractions, I need a common denominator. And I'm just going to multiply the 2 denominators to get my common one. So that's going to be x minus the quantity, x plus h, all over x times x plus h. And all of that is over my simplified denominator of h. Well, this is the same as if I simplify the top, I have x minus h over x times x plus h. And saying I divide this whole fraction on top by h is the same as multiplying by 1 over the reciprocal of h, or by multiplying by the reciprocal of h, which is 1 over h. So this gives me negative h over x times x plus h times 1 over h. The h's cancel, leaving me with negative 1 over x times x plus h. Well, for my slope, that's still for 2 points. I need to move the points infinitely close together. To move them closer, I need the limit. To say they get infinitely close means the distance between them, h, approaches 0, of -1 over x times x plus h. I can do substitution here, but please note, only h is getting replaced by 0 because this is only h that's changing. Nothing's happening to my x yet. So if h is 0, this is equal to -1 over x squared. Well, this is my slope for my function r when I don't know what x is. But I know my slope should be equal to -1/4. So if the -1 over x squared is my slope, but I'm told that should equal -1/4, so that means x squared is equal to 4. And if I take the square root, that means x is 2 or -2. And at those 2 points on my graph, I should have a slope of -1/4. And if I kind of just take a peek at my sketch, well, I could see here and here look like they have slopes of -1/4 if I draw tangent lines. Well, that would be at about positive and -2. That is a reasonable answer.